All right. So last time we were talking about the SR latch. So the SR latch is the most basic memory device because there are two input pins and two output pins. For the most part, you can look at it as only one single output pin because slash Q or not Q, NQ, is not really usually used. Sometimes it is, but most of the time it is not. Okay, and most of the time it's really just the negation of Q itself, so it's not particularly useful. But the whole point is, when both inputs are ones, it would just maintain its quote unquote current state. It can change the state if one of the inputs is a 0 and the other one is a 1. If both inputs are zeros, then both outputs would be ones. Okay, but that is not a state that an SR latch can remember. So when you transition from 0, 0 as the input to 1, 1 as the input simultaneously, then the circuitry will actually go into an oscillation mode. Because what happens is when you switch from 1, 1 to 0, 0 for the input, what happens is both of these gates will transition the output from 0 to 1. But it takes time from the time the input changes to the time that the output changes. So during that time, the output is maintained to be the same, which is 1, 1. But after a certain amount of time, which is the propagational time of one gate, then the output will change to a 0. So when the output changes to a 0, it will change the input of both gates at the same time. So both gates will now go through the same kind of delay, and then both outputs will now change to the opposite state. And we'll keep doing that. It'll keep the oscillation basically forever. It won't stop. It will stop as soon as one of the inputs is a 1 and the other one is a 0. But it won't change any further unless the input would change. So this is the simplest memory device called an SR latch. So what we'll do today is we are going to continue with the discussion of memory devices, and this time we'll start to look into D flip-flops. So in terms of the notes, we are now in the main section. It's called Von Neumann Architecture and Memory. And the notes, or the module that I'm basically reading out of, is called D flip-flop and other basic memory devices. And I'm pretty sure that's the same thing, but we'll open it here. So we are basically done with the discussion of an SR latch, and now we are moving on to a D flip-flop. So do we have any questions about the concept of an SR latch? Okay. So if the inputs are 1, 1, it maintains its state. If one is a 0, the other one is a 1, you can either make it set or reset Q. Okay. If both inputs are zeros, then both outputs would be 1s. But you don't want to transition from 0, 0 as inputs. Excuse me, you don't want, yeah, that's correct. You don't want to transition from both inputs being zeros to both inputs being 1s, because that will make the SR latch enter an oscillation state, which is usually not intended and is not good. All right? So the next concept is a D flip-flop. And this is the text representation of a D flip-flop. So what I would do is I'm going to, this class has the advantage of having the other class ahead of us, which means I have some of these circuits already drawn, although this one, okay, this one is drawn too. So this is basically a D flip-flop, not represented in text anymore, but represented in Logisim. So the first thing I would do is I'm going to turn off simulation, because this way we don't get distracted by the colors of the wires, and then we can do our analysis. First thing is the inputs are not called S and R anymore. The label of S for an SR latch is really set. Okay, that's what it means. And setting means, turning something into a 1. In this case, turning Q into a 1. R is reset. Reset means, turning something into a 0. And once again, we are turning Q into a 0. So in this notation, you can see, I have a little slash, in front of S, and a slash in front of the R, and a slash in front of the Q. A slash, when you use circuitry documentation, a slash or an overbar, they both mean negation. Okay, so when we know negation when it comes to output. So this is Q, and this is the negation of Q. That's pretty easy to understand. But what about the inputs? Why would have the input labeled as a negation? It's because it is called active low. So in this case, S and R are both active low signals or active low inputs. What does it mean when it's active low? Normally, we talk about circuits, it is active high, which means when it's a 0, we don't mean to do anything, nothing to be done, don't do anything. When it's a 1, then we say, yes, go ahead and blah, 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 do something. Okay? In this case, it is the opposite. Okay? It is called active low. It's kind of like a P-channel transistor, where when the input is a low, you turn on the device. It allows flow, but when the input is high, it is like, okay, don't do anything, break the circuit. Okay? So it's kind of the same thing. So in this sense, slash S means if you want to set Q, if you want to turn Q from whatever into a 1, you want slash S to be a 0. Okay? Because it's an active low signal, so when it is low, it means, yes, I want to do it. Same thing applies to R. If you want to reset Q, you want slash R to be a 0 instead of a 1, because it's an active low signal. So this is just an explanation of the nomenclature, what the slash really means, because it's fairly commonly used in the destination or the labeling of pins of chips. So are there any questions about the labeling of the SR latch? Questions about that? Question? Nope. Yes?
The slash is essentially the same thing as the exclamation mark?
Yes. Yep, exactly. So the slash is the same thing as an exclamation point in C and C++. And they also, sometimes people use an overbar to also mean negation. When you look at the documentation of circuitry, sometimes they use an overbar, and other times they use a slash. So there are multiple ways to indicate something is the negation of something else. Okay, very good. All right, so moving on. So instead of using S and R as the direct input, you can see the SR latch is a component. In other words, we are building some additional circuitry around an SR latch. But the SR latch in this case is really still the core of how we quote unquote remember things. But when you look at the input pins or the actual interface to this circuitry, one is labeled D, which stands for data, and the other one is labeled EN, which stands for enable. And you can see EN does not have a slash in front of it, so it is not active low. When EN is low, it means it is not enabled. When EN is high, it means it is enabled. Okay. So the first thing we want to know is, okay, what does EN do? When EN is 0, what happens to the rest of the circuitry? So we take a look at EN. Okay. So one really neat trick, if you have a circuit already entered into Logisim, is to use the little poke tool here, but not to poke the input pins to change the state, but to poke a wire or a node so that the entire node is highlighted. This makes it easy to see, how pins are connected, between the components. So now we can see EN is connected to one input of N2. It's also connected to one input of N1. Now, N1 and N2 are NAND gates, which means if at least one input is a 0, the output is going to be a 1. Okay? So that means whenever EN is a 0, N1 and N2 is going to, they're both going to output 1s. And those 1s are going into slash S and slash R. Now, because slash S and slash R are active low input pins, that means if they're high, that means we are not asking the SR latch to do anything, which basically means maintain your current state. Whatever it was, just maintain it. Is that okay? So that means whatever D is going to be completely ignored. Okay? when En is a 0, you can flip D any way you want. It's not going to have any impact or changes to the SR latch. And that is why En is called the enable pin, because when En is a 0, the device itself is disabled and it's not going to do a single thing. It will just maintain its current state. So are we good so far with this analysis when En is a 0? What happens when En is a 1? Well, let's check it out. When En is a 1, okay, looking at the thick wires again, then one input of N2 is going to be a 1. One input of N1 is also going to be a 1, which means the other pin now decides what the output of the NAND gates are going to be, right? Okay, so what is the other pin connected to? Now you have to look at D. D is going through a NOT gate, and before it goes into the NOT gate, it goes into N1. After it goes into the NOT gate, it goes to N2. In other words, N1 is experiencing exactly what D is having, and then N2 is experiencing the negation of what D is doing. So now we have to think of the two cases. What if D is 0 when En is a 1? Well, let's think about it. When D is a 0 and En is a 1, that means N1 is going to output a 1, okay? So that 1 is going to /S, which means do not set the SR latch, okay? But what about N2? When D is a 0, the negation of that is going to be a 1. That 1 is going to the other input of N2. En is 1 already, so now N2 has both inputs being 1s, which means the output is going to be a 0. That 0 is going to /R, which means we are telling the SR latch to reset Q. So now Q is going to be a 0, just like D. Now, what if it is the other way around? En is a 1 and D is also a 1. Well, the circuitry is somewhat symmetric, right? So if D is a 1, that this time N1 is going to output a 1, output a 0, which is going to /S of the SR latch. So that means the SR latch is going to set the Q pin. The Q pin becomes a 1 in order to mirror what D is experiencing. But you can also track now what's going to be available at /R. When D is 1, the negation of 1 is a 0. That 0 is going into N2. So N2 is going to output a high, which means /R is going to be a 1. So that means we are only going to set the output pin Q, but the NQ would be the opposite of that. Is that okay? So we can keep talking, but we can also just kind of play with this circuitry. Huh? What is the square?
Yeah, is it a gate or?
This is a SR latch, which is built out of this. So this is the SR latch. So now we can go ahead and play with it. So we'll go back and re-enable the circuitry. Now, as soon as I enable it, you can see the SR latch is outputting error states. It's not surprising because as soon as we turn it on, both inputs to the SR latch are going to be 1s, which is telling the SR latch to maintain its current state. But what was the previous state? Unknown. We didn't specify anything. We just say start simulation. But what was the state of the SR latch before the simulation? We didn't specify. So that's why the simulator is going like, you asked me to maintain the current state, but I don't know what the current state is. So that's why you see the errors. But that's fine, because we can change that pretty soon. So you can also see that by flipping the D pin, nothing is going to happen, okay? But as soon as you change En from a 0 to a 1, then it goes like bam, okay? The Q of the SR latch is now mirroring what D is. So as long as En is on, I can now change the D pin, and the Q pin is going to mirror, just like that. But if I turn off the enable, then nothing is going to happen when I click on the D pin. So this is the most basic D flip-flop. And the reason why it's called a D flip-flop is because instead of having one pin to say set, the other pin to say reset, which is the job of an SR latch, now we have also two pins, but one pin specifies, should I change? Should I, mirror the pin D, and then the D pin is saying what should be stored. Should I store a 0 or should I store a 1? Is that okay? So this is one of the most basic memory devices that separates what information needs to be stored from when it should be stored. Is that okay? All right, cool. So getting back to the notes, we are now moving on to the next type of flip-flop, which is called an edge-sensitive D flip-flop. So once again, we have the text representation, but since I taught exactly the same thing yesterday with the Tuesday class, that means we can just kind of go back and look at the diagram of this circuitry. So once again, I'm going to disable simulation, reset, and this time we go to the clocked D flip-flop. And it looks a little bit ugly, partially it has to do with how I placed the components, okay? So the routing of the component looks a little bit ugly. But this time you look at this and go like, this is a little bit more complex compared to the previous D flip-flop, because look at the components. We still only have 2 NAND gates, but see, one of the NAND gates actually has 3 inputs instead of 2. And we have 1 extra SR latch. We have 2 SR latches in this particular design. One is called S, one is called C, and then the NAND gates, one is called N1, the one with 3 inputs. The other one is called N2. The NOT gate is not here anymore. The NOT gate is not here anymore. But you can also see the label is different. Boba Fett subscribed to your channel. Very nice. I am definitely building the empire. All right, so this is an interesting circuit because it's called edge sensitive. So let's go ahead and analyze this circuitry and see what's going to happen. Now this is all done in text anyway, but I do want to go through this just kind of mentally, just so that we can figure out what it does. Okay, so clock is now a 0. Okay, CLK stands for clock, and data is also a 0 at this point. So we want to find out when clock is a 0, what's going to happen just because clock is a 0, regardless of what data is. When clock is 0, it's going to force N1 to output a 1, regardless of the 2 other inputs of N1, because N1 is a NAND gate. If at least one input of a NAND gate is a 0, the output is going to be a 1, right? Okay, so N1 is going to output a 1, and we'll track down where that 1 is going to. So we click on the wire, this wire here. Also now what it is highlighting is called a node, and this is an electrical node, which is something that is conducting electricity between all the contact points. It has 3 contact points. The first contact point is the output of N1. It is a 1, and that 1 is going to 2 places. It's going to N2. It's also going to the R pin of the C SR latch. If you output a 1 to /R of an SR latch, it's basically saying, don't reset, okay? But it doesn't say anything about setting or not. It simply says, do not reset, okay? It also goes to N2. So when it goes to N2, and it is a 1, so that means the state of N2 now depends entirely on data, okay? So now we have to look at the 2 cases, okay? Data can be 0, data can be 1. When data is 0, which is what it is now, then you have a 0 into N2. N2 is going to output high. That high, let me highlight which wire we are talking about. This wire, or this node, this is going to be high, and it is going into /S. It's also going into the other input of N1, but the other input of N1 is not going to be impacted anyway because it's already outputting a 1. Okay? So this 1 is basically saying, it's telling the SR latch S and say, do not set. Okay? But it doesn't say anything about resetting or not. It simply says, do not set. Okay. Let's see. And that's the extent of the effect of this pin. But there's one more thing that I forgot to mention, because clock, CLK, if you look at this note here, it goes into N1, which we talked about already, but it also goes directly into /R of the SR latch. Now that is kind of important because when /R is a 0, it means reset. Okay? So what reset is going to do is to turn Q into a 0, but /Q is going to be turned into a 1. Where's that 1 going? Well, let's click on that wire and track it down. So that 1, first it goes back to N1, which is irrelevant because N1 is going to output a 1 anyway. The other place it's going to is /S of C, but remember it's outputting a 1. So now we can see that the C SR latch is seeing both inputs being 1s, which means it is just maintaining its current state and it's not going to do anything. Okay? The other scenario is, what if data is a 1? Clock is still a 0. So if data is a 1, then N2 only depends on the wire that is coming out of N1. N1 is outputting a 1 anyway, so we have 1, 1 for N2. The output of N2 is going to be a 0. So 0 is kind of important because that 0 does go into /S. So /S is going to be a 0, which means set Q. So that not Q becomes a 0. /Q becomes a 0. It is going into here. And let's see. So it will set the Q pin. Okay, this is where I made a mistake yesterday with the other class. Okay, so let me reanalyze this one here. So we said that data is going to be a 1. This is going to be a 1 for sure because /R is, okay, I know exactly what the mistake was. Okay, so /R is going to be a 1, which means we are not doing anything with, we're not resetting Q of C. But we also know that clock is going to /R, which means for this particular SR latch, it is resetting anyway. If it's resetting, Q is going to be a 0, /Q is going to be a 1, this one is going to come down here. So regardless of what data is, the C SR latch is seeing both inputs being 1s, which means it's just maintaining its current state. Okay? Is that okay? So now we look at the transition. Okay, so this is the big difference between a clocked or edge sensitive D flip-flop compared to a regular D flip-flop that is not edge sensitive. So what we want to do now is to say, what happens when clock goes from 0 to 1? Okay, what happens at exactly that particular moment? And we can just assume data is a 0 for now, and we are saying, okay, we're transitioning clock from 0 to a 1. So we want to analyze what is going to happen at exactly that moment. So to analyze that moment, the first thing we need to do is to say, okay, so when clock is a 0, what are the current states of all the pins? So it would be nice to be able to label all of those pins. So let me see what is the best way to do this. The text description in the notes actually describes all of this stuff already. But since I'm using Logisim to describe it, I want to see if I can figure out an easy way. Not so much easy, but a handy way to do it. Let's see. We can simulate. Okay, that will work. Yep. Okay, there we go. So once again, forget about the E, the error coming out of the C SR latch, because when we turn on the simulation, the CSR latch did not really have a predefined current state. So when we ask the CSR latch to maintain its current state, it goes like, what current state are we talking about? And that's why we have this error pin here. So forget about that one. It's not that important. But what is important is we look at what happens when the clock goes from 0 to 1. What do you think is going to be the biggest change? It's going to have an immediate impact on two things. So which two things does it have an immediate impact on? If you just track down that node. Okay, so we track down this node and go like, oh, N1 is going to change. The output of N1 is going to change from a 1 to a 0 because once clock goes from 0 to 1, right at that moment, N1, after a very short amount of time, N1 is going to output a 0. And where is that 0 going to? That 0 is going to two places. It's going to N2. So that 0 is going to N2. So N2 is going to be forced to output a 1. And that 1 is going to /s, which doesn't do anything to the SSR latch. Nope. No, it's a 0. So this is going to be a 1. No, it's correct. It's correct because the output of N1 will switch into a 0. So that 0 going to N2 is just going to make N2 output a 1, which it is already outputting. So that means the SSR latch is not going to be set. Yep.
Why will the output of N1 switch?
Because when clock is 1, then you will have all three inputs being 1s. And this is a NAND gate, which means if all the inputs are 1s, the output is going to be a 0. Okay, but it also has an impact, potential impact on the CSR latch. Because in this case, you can see how the output of N1 is going to the /R of the CSR latch, which means the CSR latch is going to reset, which also means the Q pin is going to be a 0. So we change the state of the actual memory SR latch, which is the CSR latch, to a 0. Okay, is that analysis working? Okay, so we'll go ahead and actually do that. Okay, so we'll go clock switches from 0 to a 1, and you can see that's exactly what happened. Okay, we anticipated this to be what's going to happen. Now this is called a okay, you might think, but the previous circuit would do the same thing. The previous circuit, if I use the enable pin instead of the clock pin, that's exactly what's going to happen too, because when we turn the enable pin from a 0 to a 1, then the device will pay attention to the D pin and change the SR latch. So from this perspective up to this point, this more complex design doesn't seem to behave any differently compared to the previous design. But what is going to be interesting now is, okay, now that the clock pin is a 1, what happens when I change the data pin? What do you think is going to happen? So I will maintain the clock to be a 1, but I will just go ahead and switch the data pin. Do you think anything really important is going to happen? See the other input of N2? That's already a 0. So by changing the data pin from 0 to 1, the only change is just that one single wire, because N2 already has one input being a 0, which means if the other input becomes, whether it's a 0 or 1, is not relevant. So there's no change. Okay, so just to confirm that, go like, hey, look at this. Nothing happens to the output. This is one big difference compared to the previous design. Because in the previous design, as long as the EN pin, the enable pin, is a 1, every time I change the data input pin, the output is going to change. This one says, nope. Once the clock pin is turned into a 1, it doesn't pay attention to the data pin anymore. Okay? All right. So the output pin is now a 0. So we'll do something funky and say, okay, let's see if I can turn the data pin to a 1. And what happens when I turn the clock pin from 1 back to a 0? Is that going to affect the output pin Q from the entire design? So that's the next question. So let's see what happens when we switch the clock pin from a 1 back to a 0. When you switch clock from a 1 to a 0, let's see where that wire is going, what this node is connecting. So it will impact two things at the same time. It's going to impact N1 because N1 is going to output a 1. That 1 is going to go to /R, and that by itself is not going to do a single thing because having a 1 to /R of an SR latch is saying, don't do anything, do not reset, okay? So that's not going to have any effect. The other place that is going to is straight into /R of the S pin. So that's going to do something because it's going to reset the Q of the SR latch. But when you reset Q, then /Q is going to be a 1, which means this wire will still maintain to be a 1. So in that case, C as an SR latch is going to see both inputs being a 1, which means do not make any changes, maintain your current state. Is that making any sense? Which basically means, yeah, you can put a 1 in an input pin called data, but when your clock is transitioning from 1 back to 0, it's not going to change the actual output. Is that okay? So let's check it out. So clock is now switching from a 1 back to a 0, and you can see exactly that's happening. The C SR latch is now seeing both inputs being 1s, which means to the SR latch, maintain your current state, don't do anything. Is that okay? So now we want to go from 0 back to a 1, with a clock pin, but data pin is now a 1. And we want to see, okay, what's going to happen this time? So what do you think is going to happen if I click on the clock input pin so it switches from 0 back into a 1? The output would change, but why is it changing, right? So let's try to follow the logic here. So we are talking about this node going from a 0 back to a 1, and then we will see what that is going to impact. So it goes into N1, and N1 still has one input being a 0, so N1 will continue to output a 1 as far as N1 is concerned. The other wire is going to /R. Now, that is kind of important because right now, the SR latch has both inputs being 0s, which means both outputs, Q and /Q, are 1s. As soon as clock goes from 0 to 1, /R is going to go from a 0 to a 1, which means /S is the only pin being a 0, which means we are now telling the SR latch to set the Q pin, which means the /Q is going to be a 0 this time. So we look at this /Q pin, it's going to be a 0, and see what happens when that is happening. So we are talking about this pin here, or this node, going from 1 to 0. When this goes from 1 to 0, the first place it goes to is the C SR latch. So the C SR latch is going to see /S going from 1 to a 0, which means, hey, set Q pin. So the Q pin is going to go from a 0 to a 1. But where else is it going? It's also going back to the N1 NAND gate. So now we have the N1 will still be outputting the same thing because clock is a 1. Clock is a 1, and so it will still maintain the output to be a 0. And that's the extent of the analysis. So let's go ahead and check whether that is the case or not. So now we go to the clock pin, and we switch the clock pin from a 0 back to a 1. And you can see that's exactly what happened. The output of M1 maintains to be a 1, but the /Q of the SR latch becomes a 0, and that feeds into the /S pin of the C SR latch, which causes the C SR latch to now say, okay, my output is now a 1. Is that okay? Yep. At this point? Yeah. Well, let's see what happens, okay? But I'm not going to click it. I'm just going to analyze it, okay? So what happens when data goes from a 1 to a 0 at this point? What's going to happen? So we are tracking down this pin and say, what if this goes from a 1 to a 0? if this goes from a 1 to a 0, this is going to be a 1, right? That's the immediate change to N2. So what happens when this goes from a 0 to a 1? The SSR latch just says, okay, I'm just going to maintain the current state, which means I will continue to output a 0 with /q, right? It's also going to N1, okay? But that's okay because N1 is, okay, let me take a look at this. It's fine. Okay, this is fine. So the SSR latch will continue to output a 0. And then /s is going to be a 1. That's fine. And the third input of N1 is also going to be a 1. But because the output of the SSR latch is outputting a 0, so N1 itself will continue to output a 1. So that part does not change. And as a result, there's no change to the CSR latch. The CSR latch will continue to see a 0 from the S/S pin and a 1 from the /R pin. So it will still maintain its state. It's not going to turn into a 0. Okay, sure. But we'll do it just to make sure. And that's exactly what I said. Yep. So that means, it's only at the very moment of the clock pin going from a 0 to a 1 that it will actually pay attention to the data pin and change the output Q of the entire design to mirror whatever the data pin is. But only at that very instant. Only at the time that you see a rising edge with a clock pin. Any other time, it ignores the data pin. Is that okay? So this is a very different design compared to the previous one. The previous one is what we call a level sensitive design, which means as long as the EM pin is a 1, the output is going to mirror the input. This one is what we call an edge sensitive, or otherwise known as a clocked design. Okay, sorry, no drink in the class. Because the lab manager actually nailed one instructor for drinking coffee at the instructor workstation. Now, in that particular case, it was really bad because they found the keyboard and the mouse swimming in coffee when they came in to clean it up. So anyway, this one is what we call an edge sensitive or a clocked circuit, which basically means there's a very short amount of time when the output is going to mirror the input. It is only during the time of the transition. Okay? So is that okay so far with this? Yep.
Can you click on the SR latch? Just I want to see the labeling.
The SR latch. Which one?
One of
Huh?
yeah.
Okay. And oh, you mean the properties? Yeah, so I can name them because they have a label. Yep. So are we good with this? All right, so moving on. So the next one is in the notes only. I did not make a... So this is the analysis of what happens when the clock changes or when it's steady. Okay, so this is the next one. Looks kind of about the same in terms of complexity compared to the previous one, but this one has got 3 SR latches. The previous one only has 2. This one has got 3 SR latches. So we got SR latch SR1, SR latch SR2, and SR latch SRC. And then we have 2 NAND gates, AND gates, sorry. This time they're AND gates. They do not have a little bubble at the output, so they're just regular AND gates. So we got A1 and A2 as regular AND gates. One has 2 input, the other one has 3 input. So the analysis of the circuitry is described in the text here. But what I want to do is to say, but what does this do? Okay, Now, we can go through the same analysis, or you can read through the analysis to find out exactly what it does. But just from the naming of the pins, I think you got an idea of what it does. It has a data pin. It has got an EN for enable, just like the design before the previous one. And it has got a clock pin, just like the previous design. So this is basically a hybrid between the two D flip-flops that we had talked about earlier. In other words, it has the enable being a level sensitive thing, and it has a clock being an edge sensitive thing. It has both. So in order for this particular design to mirror the input to the output, two conditions must be met. One is the enable pin has to be a 1. And two, the clock pin has to be on the rising edge. Is that okay? So it is both. So in this particular sense, the enable pin, you can call it what we call a gated design. Okay, it's gated by the EN pin. If the EN pin is a 0, you can clock all day long and nothing happens. At the same time, if the EN pin is high, but the clock pin is not having a 0 to 1 or rising edge, nothing is going to happen. So you need two conditions to be present at the same time in order for the device to change its output to the input, which is data. So you will ask, why do we need something like this? Okay, well, I can answer that question. So think about yourself, as the person at the entrance of Costco. Okay, if you have been to a Costco, you know there's a guy who has a little counter thing to count the people coming in, right? But think about, in this case, you have basically two counters. One counter to count the number of people holding a membership card, and the other counter to count everybody else. So people, the family members, friends, colleagues, who are just following the person with a card. Okay, so now you have two counters, but you only got one clicker. Okay, you got one clicker, two counters. So what are you going to do, in this case? Well, this is what's going to happen. When you click, that's your clock line. Okay, so the moment you do this click, it's the same thing as a rising edge. The counter is going like, okay, I can now increment. But you also have a foot switch. So you have two foot switches. One foot switch for members, one foot switch for non-members. Okay? And now each foot switch connects to an actual counter on the floor. Okay, can you guys kind of imagine that scenario? Okay? All right, so you see somebody walking in with a membership card. Okay, so what do? You step on the counter that says members, and then you click. That counter goes like increments. Okay, and then you step off the foot paddle. Then you see 3 people coming in after that person with no membership cards. What do? You step on the foot paddle that says non-members, and then you click 3 times. 1, 2, 3. You only got one clicker, but you have 2 foot paddles to select which counter should increment. That is the whole point of having both of these. EN allows us to say who is paying attention. And then the clock line is saying when to do something. So one controls who, the other one controls when. And with both of these pins, we have now control over both things. Okay, member or non-member, and when to increment. Is that okay? Yep.
So the enable was member or non-member, right, in this case?
Mm-hmm.
And then the clock is just
No, you have 2 devices now. You have 2 devices. One device is labeled member, the other device is labeled non-member. They have their clocks hooked up to exactly the same clicker that you have, but the EN is separate. One EN goes to the foot paddle that says members, and then the other goes to the foot paddle that says non-members. Okay? So this is the next design. I'm not going to go through the analysis of the circuit. It is all kind of written here. So you can see how this is all written. And then we have one last one that's even bigger. So when you look at this one, you go like, well, we got three SR latches, SR1, SR2, SR3. We have two AND gates, A1, A2, just like the previous one. But now we also have an OR gate that looks kind of funky. It has one input is negated, and we have A3, which is another AND gate, which I think is missing in the previous design. But when you look at the pins, okay, which is the interface to the design, you go like, okay, so if we don't care about what is inside the device and just look at the pins, how is this different from the previous one? We got clock, just like the previous one. We got EN, just like the previous one. We got data, just like the previous one. Oh, but this time we have an extra input pin called reset. Okay, so what is reset going to do? Well, okay, all you have to see is to track down where reset is going. So reset is going to these two devices. One is an OR gate, one is an AND gate. What happens when reset becomes a 1? What do you think? When reset is a 1, then the negation of 1 becomes a 0. So O1 is going to see a 0 from here. And reset is going to be a 1 to A3. A3 is an AND gate. So the AND gate is going to be, okay, reset is active low. I forgot to put a slash in front of it. So that's why it doesn't make sense to me. So, okay, so reset has a slash in front of it, which means it is active low. When reset is high, don't do a single thing. When reset is low, we want something to happen. So it is the analysis of when reset is low that is important. Okay, so let's do this one more time. Reset is low. Reset is a 0. It goes into these two things. The first thing it does is we take the negation of 0, we put it into an OR gate. What's going to happen to the OR gate? The output of the OR gate is going to be a 1. Very good. That one goes to the S of the SRC latch. SRC SR latch. What happens to the AND gate? The AND gate is seeing the non-negative version of reset, and reset is 0. So what happens when the input of a regular AND gate is a 0? What is the output? So it's going to be a 0. So the 0 is going to go to the reset of the SR latch. So that means the output is going to be reset to a 0. So that is independent to all the rest of the circuitry, because this circuitry is closer to the SR latch than all of the other circuitry, which basically means you can be clocking, you can be enabled or not enabled, the data can be a 0 or 1, nothing matters. As soon as reset goes from a 1 to a 0, the final SR latch, SRC, is going to switch to a 0. Why don't we need that? This is going to help us fix that problem that we saw earlier. When you first turn on the computer and you say, hey, SR latches, go maintain your current state, what are they going to do? They're going to go like, okay, I'll pick a random state to maintain. Fine. Okay, it can be a 1, can be a 0. Whether it's a 1 or a 0 depends on whether you're running your microwave or not, whether you're using a cell phone next to it or not, who you're talking to on the cell phone, and so on and so forth. Do we want computers to have its memory initialized to some random things at the beginning? Probably not. So this is why we need this particular reset pin, so that we can say, oh, you are just powering up. Hold the reset pin for X many milliseconds. So all the devices, not just memory, every single device, your processor, your chipsets, all the PCI cards that you have installed, everything in your computer they're all connected to a system-wide reset pin. When the reset pin is a 0, it's telling all the devices in your computer to go to your reset state. Everybody, go to your reset state. Is that okay? But hold on a second here. There's a chicken and egg problem. So if the computer itself is just powering up, who is in charge of the reset pin to make sure that everybody else is going to reset?
Is it like the power switch itself?
It's actually a special chip on the circuit board. It's called a supervisor. It's called a supervisor chip. It's one of its main job is to do a power up reset. So when it sees the power, going up from a brownout level to a healthy voltage, it will hold the reset pin for X amount of time, which is usually in tens of milliseconds, which in a computer's time frame is like really, really long. Most devices only takes like microseconds to reset, but it will hold it on for like milliseconds just to make sure that everybody has a chance to reset. It's called a supervisor chip. The supervisor chip does several things. Okay, do you guys know what is a brownout as opposed to a blackout? A blackout is easy. Okay, there's no power. Power went from 110 volts to 0. Okay, that's a blackout. Blackout is not too much of a problem because everything shuts down at the same time and your computer stops working. A brownout, on the other hand, is a it's a decrease of voltage. So when you look at the wall outlet, which normally should be 110 volts AC, it went down to maybe 40, 50, and it fluctuates a little bit like that. It's called a brownout because, in the good old days when we had incandescent light bulbs, those light bulbs would just kind of dim, but it won't go out completely. Okay, so it's called a brownout. So a brownout is really bad because some devices may still have enough voltage to operate, and other devices goes like, okay, I'm crapping out because there's not enough juice for me to work. So now you have part of your computer still working and part of your computer not working, and that can really cause a lot of problems. Because what if your SATA controller says, I still got enough juice, I can still run the hard drive. Your main processor goes like, I'm going into coma, okay? But before I enter a coma, I'm telling the SATA controller and go like, just wipe everything with a 0, right? That would not be a good thing because the next time you power your computer, you're going to have a lot of lost sectors because the SATA controller is not out yet, and then your main processor, the last thing it did was to say, just wipe everything. That wouldn't be good. So one of the job of the supervisor chip is to monitor that voltage and go, if it dips below, what is considered a healthy voltage, hold that reset line again. Okay, so what that's going to do is to say, even when the voltage is relatively healthy, is telling the processor, the SATA controller, and everybody else, and just go like, stop. Okay, now can you lose one sector because of that? Absolutely. Okay, because if the SATA controller is in the process of writing one sector on your hard drive, you will lose that sector, one sector, but you're not going to lose any more than one sector because the processor can no longer tell the SATA controller to do something stupid after that. Is that okay? There's one more job for that supervisor chip. Have you guys seen or have heard of the blue screen of death in Windows? When does it happen? Not during boot. It's supposed to be a pretty bad thing. Okay, you guys have seen not segmentation faults. It's called when the program crashes in Windows. Okay, it gives you a little pop-up box and go like, oh, this program just died, right? But the rest of your system is still up and running. So when you get the blue screen of death when the kernel itself is in big trouble and nobody can rescue it. You cannot get into the task manager and find out, okay, which process is taking up too much time and kill that process. You have no control whatsoever. The system, quote unquote, locked up. Okay? So the supervisor chip has what we call a watchdog mechanism. A watchdog mechanism is kind of like a dead man switch. Okay? So the watchdog mechanism says, okay, I'm making this assumption. When the system is healthy, somebody is going to give me I'm still good signal every, I don't know, let's call that 5 seconds. Okay? So every 5 seconds, I'm expecting the operating system to confirm with me that everything is still good. Is that okay? So let's say 5 seconds, 10 seconds went by, I did not get a confirmation that everything is still good. That watchdog is going to go off. It's a timer. So it's going to go off and say, something bad has just happened. Okay? And that signal goes into what we call an NMI line of the main processor. NMI stands for non-maskable interrupt. It cannot be stopped. It goes into the processor. And then the processor now goes into panic mode and say, holy beep, something bad just happened. Something really, really bad happened. And that's when that will enter the blue screen of death, which is basically the very last resort, okay, that your operating system has to say, something really bad happened. All I can do is to give you a dump of some numbers on the screen, potentially a dump of the memory content onto the hard drive, and that's it. Okay, I cannot do anything further than this. That's also the job of the supervisor chip. So I'm just telling you all these things, because it's sort of related to the reset line, but but they're all inside your processor and also your phones. Okay, your Android phone and your iOS phones, they have the same kind of mechanism. So sometimes when your phone enters a really bad state, it will reset itself, and that's because of the watchdog mechanism not getting confirmation that everything is still good. So it just instructs the phone to reboot itself. Cool. All right. So this is the very last thing. So if you look at this thing and turn it into one single device with 4 input pins, now we can just hook up a whole bunch of these things. Okay, and look at this design here. What does it look like to you? Each one, each box here is a D flip-flop, the most complicated D flip-flop that we just talked about. Okay, you can see they share a lot of lines. Okay, what lines are shared? Look at all those dots. Okay, they're indicating a line is shared. So when you look at it, what about the clock line? The clock line goes to everybody. It is shared. Okay, what about the enable line? The enable line is also shared. What about the reset line? The reset line is also shared. So the 3 control pins are shared amongst all of these D flip-flops. What is not shared? The data pin. That's it. The data pin is the only thing that is not shared. The input is an 8-bit data pin. I use a splitter, split it into 8 individual wires. Each wire goes into only one single device, because one device is only capable of remembering 1 bit. Okay? So what about the output of these things? The output of all of these things combined through a merger, which is basically the reverse direction of a splitter, into an output pin. Is that okay? And what do we call 8 bits together? A byte. Very good. So together, this design is a byte-wide D flip-flop. It is resettable, it is gated, and it is edge sensitive. So let's recall what this device is, how we call this device. Okay, it is a resettable, gated, clocked, byte-wide D flip-flop. Now, if I have to repeat what I just said, many times in each class, that would be a waste of time. So let's just call it a register. Okay? Because that basically is what a register is. A register is a bank of bit D flip-flops, and each D flip-flop is resettable, gated, and clocked. Yep.
So all these boxes right here, those are deep flip-flops?
Yes. So each one of these D flip-flops is actually this. Yep. And then together, this entire thing is called a register. So in Logisim, where do we get a register? So if you go into Logisim, I'm going to start a new circuit here. Okay, we'll just call this one test. Okay, and we go to memory, And here's our register. So you pop a register in, and what do we recognize? There are a few things that are pretty stand out and go like, yeah, we see those things. We have seen those things for the past hour or so, right? There's D, which is data. That's the input. There's Q, which is the output. Okay. There's EN, the enable pin. Okay. The reset pin is labeled 0 because RESET takes up too much space. 0 doesn't take up much space. The only one that we haven't really seen is, what is that little triangle thing? That's the clock. So we have exactly the same pins in the register, except this one is just one single unit. So are we okay at this point, in terms of understanding what a register really is? A register, when you expand it, it is a bank of individual bit D flip-flops. Each D flip-flop is resettable, gated, and clocked. That's what a register is. So when you look at the properties of a register, you can change the number of bits if you want to. So if you click on that, okay, so let's go ahead and do that. So when you click on data bits, you can go all the way back to 0, back to 1, which turns it back into just a regular D flip-flop, okay, single bit D flip-flop. But the usual one is 8, which is a byte wide. You can even change the trigger. So the trigger itself, which is the clock line, can be sensitive to rising edge, falling edge, or can be level sensitive. We don't want it to be level sensitive. We want it to be rising edge. Okay, so in this class, most registers are rising edge sensitive. We can give it a label and the font, so those things are not relevant. We still have about 20 minutes left, well, maybe 15 or so. So now the question is, okay, cool, now we have a register. What can we do with a register, right? Well, remember that counter thing? Let's see if we can use a register in combination with an adder so that we can say, yep, count, click, 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 increment, increment. Okay, is that making any sense? All right, so let's try that. So we'll keep it as an 8-bit device. So this is the register, and then we'll pick out an adder. An adder goes to arithmetic. So here's this is our adder. Okay. So when you look at the adder, the only thing you can change is the data bits. 8-bit is what we want because we want these two to have the same. So you probably can imagine what needs to happen here. The output of the adder has to go to the input of the register. The output of the register is going to go back to the input of the adder. Now the adder has two inputs. This is the first input, and there's the second input. There are three, okay, I take it back. There are 3 inputs to an adder because you have X, Y, and then carry in, okay, or K0 in our notation. So we'll just go like, okay, we'll make one of these ones. So we pick out a constant from wiring, and we just say, we'll make the carry always a 1. And then we'll make a 0 as the other number, so y is always a 0. So we go to constant again, but this time I need some adjustments because we'll need an 8-bit 0 as a constant. Okay, so this constant goes to the other input of the adder, like that. So now we have the most basic stuff hooked up. There are a few other things that need to hook up as well. So what's happening is the adder is always looking at the input and changing the output accordingly. So if the input is a 0, the output is going to be a 1. If the input is a 1, the output is always going to be a 2. And it has no clock line, has no enable line, it's always on. Okay, it's always doing computation. The register, on the other hand, is a clocked device, which means, well, if it's not transitioning from a 0 to 1 at the clock line, it's not going to do anything. It's like, okay, I'm just going to output 0. Okay, so this 0 is going into this wire, going into the input of the adder. The output of the adder is going to be a 1 at this point, but the register is saying, nobody tells me to pay attention to the input line, so I'm going to ignore that. Is that okay? You can actually see that happening even now. So you can go to simulate enabled. Okay, so everything is actually running right now. So if you click on this wire, which is the output of the register, this is the actual content of the register. So the output of the register is always matching the content of the register. Okay, no big deal. We kind of know that, right? The adder is always working. In other words, it's outputting a 1 already. But nothing is happening at this point because the register says, by default, I'm not paying attention. Okay, so if that is not paying attention, let's see what we can do with the register. The first thing we want to do is, well, we can hook up just pins. And there are other things that are really cool to have too. So if you go to input output, they have some really kind of interesting stuff like buttons. Okay, so we'll go ahead and use some buttons here. And here's one button for the reset line. And we'll make the button face north so the pin is up. So this is our reset pin. When I click this button, it will reset the register. And then this is the enable. And we'll say the device is always enabled. Oops. Let's see. Put this back here. And this is the clock line. So for the clock line, what we can do is, I'm thinking about using an actual clock line, in which we can. So let's use an actual clock line here. Okay, so we go back to wiring, and then we pick out a clock. There we go. So we hook up the clock to the clock pin here. Okay. So now there are several things we can do. Okay, if you do not like 0, 0 as the initial value of a register, you can always change that. You can just click on, I think using this tool, click on here, and you can just type in the new value. It's in hexadecimal, so if I want it to be 5F, I can turn it into 5F. So 5F is going to be a 01011111, so the output should have that particular bit pattern. Let's check that first. Okay, so the output is in fact, okay, 01011111, which means the output of the adder is going to be 0110 and then all zeros, just like that. Okay, so we know this part is working, which is kind of cool. So now we say, so how do we make an increment? To make an increment, all you have to do is to click on the clock line. So the clock line is what we call a toggle. So if it is low, the next click is going to turn it high. If it is high, the next click is going to turn it low. So you can see how now it's high, but because the register is rising edge sensitive, the moment I have a rising edge on the clock line, it looks at the input, which was already 60 in hexadecimal, and say, oh, okay, you want me to remember that. Okay, no problem. Okay, so now the output of the register is going to be 60 in hexadecimal. The output of the adder is going to be 61 in hexadecimal. Okay, so the next click of the clock line is going to be a falling edge, which the register is going to ignore, like that. And then the next one is going to increment it to 61. And then ignore the falling edge, rising edge, 6.2, falling edge, ignored, and so on. Okay? What if I want to do this many times? Because, this is the basic heartbeat of your computer. Okay? There's a clock that is universal to everything inside your computer, and it provides a synchronization mechanism. Okay? So in order for a simulator to work, you probably have to click on the clock line like hundreds of times, if not more, in order for a program to run. So that's rather tedious, right? I mean, you having to click on that thing like hundreds of times. So one thing we can do is to go to simulate, and you can see how it has a shortcut key for click once, which is Control T. So I could have just type Control T instead of clicking on the clock pin. But it also has ticks enabled. Now when you enable ticks, then it will automatically oscillate the clock, okay, from high to low to high to low to high to low. So this way you don't have to click like crazy. But if you say, well, I don't want it to click too fast because I can't really see what is going on if it's clicking too fast, then you go to click frequency and you say, okay, 4.1 kilohertz is a little bit too fast for me to visualize. What is a kilohertz? What is a hertz? What does it measure? It measures frequency, number of times per second. So 1 hertz means once every second, 2 hertz means twice per second, 3 hertz means 3 times per second. This means 4,100 times per second. I don't think my eyes can catch that, okay? So let's go all the way down, okay? So if you look at tick frequency and go all the way down to 0.25 hertz, what does that mean? Can we really have a fraction of a hertz? Exactly, it's once every 4 seconds. I think we can see that, okay? So we'll pick that for now. And nothing happens because I have not enabled it yet. So to enable ticks, you can either type Control K, or you can just go to the menu and select it. So now every 4 seconds, we should see a change, like that. Another 4 seconds, we'll see another change, like that, and so on. So now you can actually, by increasing the tick frequency, you can now actually see the number going up really fast, or the way it is right now, which is kind of slow. We can follow that. Is that okay so far? Hmm? Hmm?
You've made a timer.
I have made a counter. Yeah, but it's a timer because it's time-based. Correct. So it's kind of cool. Now, if I say, let's start from the beginning, I can just click on this button here, which is the reset button. Ding, back to 0. So are there any questions about this kind of little circuitry? Now, this circuitry, just for counting or for timing, would not have been possible without a clocked or an edge-sensitive D flip-flop. Because if you do not have a register in between and you just hook up the output of an adder back to the input of the adder, the adder is just going to go crazy because it will update the output based on changes to the input. And it will just do it in a continuous basis, which makes no sense, okay? Because you have no control over when it should increment, and you have no control over the actual value either. By using a register in between the output of the adder and the input of the adder, now you can say, when do I want to update? Should I update? When to reset it back to 0? Now you have full control over the counting process. So are we doing okay so far with this little circuit here? Okay, very good. Let's see, how much time do we have? We got 5 minutes. So 5 minutes is quite enough of time to demonstrate the next thing I want to show. So let me save this file. Okay, I'm gonna just save. And I'm just gonna use today's date because I don't have any really good name for this one. And today is the 10th. Okay, there we go. So what I'm going to show you next is, okay, in the notes first. Okay, so let's go back to the notes. You can see my suspension of the tabs because I tend to have like 20, 30 tabs open at the same time, and that chews up a lot of memory. So I have this little add-on here called the silence of the tabs. So what it does is, it will measure, it will look at the tabs and see which one you have not been used. It has not been used for 5 minutes. Then it will quote unquote suspend the tab, which basically will free up all the memory that have been used for that particular tab. So it really helps to manage, how much memory I have available, especially on a device without a lot of RAM to begin with. Like this thing, it only has like 4 gigs of RAM. When was the last time that you used a Windows machine that has 4 gigs of RAM? Okay, so So we are basically done with D flip-flop and other memory devices, and the clock circuit is kind of the same thing that what I just went through, which is a counter that goes up, uh, per tick, periodically. Okay, it's shown a little bit differently, okay, but it's the same circuitry. So that's basically what we have. But what I do want to show you is something. Let's see, where's my processor? Okay. Okay, there we go. Okay, this is what I want to show you because you'll be looking at this for the rest of this semester. Don't worry, you don't have to design it, it's already done. This is a processor. This is not, I take it back, this is actually a computer because this part is the memory and the rest is the processor itself. So the rest of the semester, what we'll do is, remember von Neumann? So what was his contribution again? The ability to store instructions in memory. Okay, so this is our memory. So we'll be storing instructions over here. And you can see the clock line right there. Okay, right there. So see how the clock line is going to a tunnel? Because everything, almost everything, needs to hook up to the clock line. So the clock line is shared by a register bank. A register bank is really just what the name implies, is a whole bunch of registers. It also goes into the microcode engine. The clock line goes into the microcode engine. See how we have the adder, a register, and a loop. Okay, now this one is a little bit more than a loop, but it is nonetheless the same kind of mechanism. And we see the same thing over here. See how we have the clock line, a register, an adder, and a potential path to complete the loop. Okay, we have a whole bunch of other things. We have the ALU, doing all the math stuff here, and then we have the output of the ROM. This is a ROM. We'll talk about that too. This is the ROM, and then the ROM splits into like a whole gazillion wind tunnels as well. But this is our processor. This is where we'll be writing instructions to run and to experiment and to find out, okay, so given this kind of C code, what does it translate to? How does the processor know how to perform this loop? How does the processor know how to access a parameter when you call a subroutine? How do we return a value from the subroutine? This is our playground to play with all of that stuff. Okay? Now, some of these components do not break down. They can be broken down into smaller ones, like this one. This is the register bank. So when you look at the register bank, this is what it looks like. It literally is really just a bank of registers. In this case, there are 4 registers. Okay, so A, B, C, and D are the 4 registers. They share the same common input. There are 2 possible outputs. I'll explain all of this, in another class. And then we have the ALU, which stands for the arithmetic and logic unit. This one is kind of large and complex on its own. So this is the ALU. And then when we go back to the main, so what we'll be doing, okay, let me focus on just the part that I want to show here. So what we'll be doing for the rest of this semester, okay, is to specify instructions here so that your processor can get those instructions, execute the instructions, change the registers, use the ALU for calculation, and blah, 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 blah. And then we'll be writing C code. So I'll give you the C code. You will translate it into assembly or machine code. The processor will run it, and we'll see whether your implementation matches what the C code is supposed to do. So that's what we'll be doing for the rest of the semester. So the first half of the semester is kind of like a bottom-up, view of circuitry, logic gates, devices, and so on and so forth. The second half of the class, is actually going to, oh, okay, so let's program these things. Let's see. We got, well, I'm running out of time, so I'm going to talk about the assembler next time. Okay, so none of this you have to take it too seriously at this point because we have just gone over the most basic memory devices. So make sure your reading is up to there. Okay, and then after that we'll start to introduce the processor, how it works, what each component is really doing, and stuff like that. Okay. So we'll head out to the lab because I think the positive exponent homework is still active for this class. Yep. So that's basically what we'll be doing. If you're done with that one, there's no actual work to do at the lab for now. So I'll turn off the recorder and head out to the lab.